Good morning to all. Myself Yamni. I am from CSCF section. Today my topic potentiometric sensors are and ampherometric sensors. Introduction. Electrochemical sensors convert chemical or biological information into electrical signals. They are widely used in medical, industrial and environmental applications. Two important types are potentiometric and ampherometric sensors. Electrochemical sensors overview operate based on redox reactions or potential differences. Use electrodes that interact with chemical species in a sample. Output signals depend on analyte concentration. Classification of electrochemical sensors. Potentiometric sensors measure voltage without current. Ampherometric sensors measure current from redox reactions. Conductometric sensors detect conductivity changes. Voltmetric sensors measure current at varying voltage. Potentiometric sensors definition. Measure potential between indicator and reference electrodes. No significant current flows during measurement. Potential depends on ion activity in solution. Components of potentiometric sensor. Indicator electrode. Sensitive to target ion. Reference electrode. Maintains constant potential. Ion selective membrane. Allows selective ion detection. Measuring device. Records voltage difference. Working principle potentiometric. Uses the Nernst equation E is equals to E naught plus 0.059 by N into log concentration of ion. Potential changes as ion concentration changes. Requires stable electrodes for accurate measurement. Ion selective electrodes ISE. Glass electrodes mostly for H plus ions. pH measurement. Solid state electrodes. Crystalline membranes for ions like fluorine, chlorine. Liquid membrane electrodes for selective ion binding. Polymer membrane electrodes used in multi-ion detection. Advantages of potentiometric. Highly selective, energy efficient due to low current usage. Simple concentration and easy handling. Good for long-term monitoring. Disadvantages of potentiometric. Membrane fouling affects accuracy. Temperature variations influence results. Collaboration required regularly. Slower response for some ions. Applications of potentiometric. Water quantity testing, pH, ions, clinical diagnostics, blood pH and electrolytes, soil nutrient testing in agriculture, food quantity testing, acidity control. Ampherometric sensors definition. Measure current produced by oxidation or reduction of analyte. Current is proportional to analyte concentration. Require applied voltage to derive redox reactions. Components of ampherometric sensor. Working electrode, site of oxidation or reduction. Reference electrode, controls potential. Counter electrode, complex circuit. Electrolyte, enables ion transport. Working principle ampherometric sensors. A fixed potential is applied between working and reference electrodes. Electroactive analytes undergo redox reactions that resulting electrode flow produces measurable current. Current increases with a higher analyte concentration. Modes of ampherometric operation. Constant potential ampherometry, simple and widely used. Pulsed ampherometry reduces surface fouling. Multiple pulse ampherometry allows multi-analyte detection. Examples of ampherometric sensors. Glucose sensors for diabetic monitoring, oxygen sensors for environmental and clinical use, lactate sensors for sports and medical diagnostics, toxic gas sensors, example carbon monoxide, nitrogen dioxide. Advantages of ampherometric: high sensitivity due to measurable electron flow, fast response time, capable of detecting very low analyte levels, suitable for continuous monitoring. Disadvantages of ampherometric sensors: requires power due to applied voltage, possible interference from other electroactive species, electrode fouling affects long-term stability, require, requires frequent maintenance. Applications of ampherometric: blood glucose measurement, environmental detection of pollutants, industrial fermentation monitoring, biochemical enzyme based sensing. Comparison: potentiometric versus ampherometric. Potentiometric measures voltage, ampherometric measures current. Potentiometric works without current, ampherometric needs applied voltage. Potentiometric high selectivity, ampherometric high sensitivity. Applications differ based on analyte type and required precaution. Future trends: nanomaterials for enhanced sensitivity, wearable biosensors for health monitoring, wireless and smartphone based sensors, highly miniatured MEMS based devices. Conclusion: potentiometric and ampherometric sensors are critical in analytical chemistry. Both have unique advantages suited to specific applications. Technological advancements continue to improve their performance. These sensors will remain essential in healthcare, industry, and environmental science. Thank you.